Today, I would like to discuss a rather strange argument that apparently shows that pi is equal to 4. Now, this argument has circulated around the internet for as long as I can remember. However, in case you haven't seen it, let me just quickly share it. So you start with this red circle and assume that this red circle has a radius of 1/2, which would mean its circumference, or in other words, its length, is precisely pi. And around this circle, we have a black square, and the side length of this black square will be 1, which means its perimeter is 4. Now what we're going to do next is we're going to add 4 divots to the black shape. Let me just quickly do that. Now, notice that doing this, just imagine that these divots are all at right angles, but notice that doing this does not change the length of the shape. This new black shape still has a perimeter of 4. And that's just because, if you take a rectangle and, you traverse it on the outer sides versus on the inner sides, it doesn't matter. You go the same distance. So this black shape still has a perimeter of 4 when I add these 4 divots to it. But let me just make it touch the circle at 8 more points. What about 16 more points? And remember, every single step I take does not change the perimeter of the shape. This shape I've constructed here, the black one, still has a perimeter of 4. So let's just do it again, and again, and again, and again, and again. And before you know it, to the naked eye, this shape becomes indistinguishable from a circle. So every step you take, this gets closer and closer to a circle. So you have this shape that's basically indistinguishable from a circle and has a perimeter of 4, and then you have a circle which has a perimeter of pi. So does that mean pi equals 4? Now, there are a lot of explanations out there about this apparent paradox, and I would like to think through some of them critically. Now, one explanation that I encountered repeatedly was this idea that this black shape that I've constructed over here is never actually a circle. So the definition of a circle is, all the points are at the same distance from one chosen point. And that will never be true for this shape, no matter how many steps I take. I could take 4, I could take 100, I could take 1,000. No matter how close it looks visually to a circle, it will never actually be a circle, so we should not expect that its length should be the same as a circle. Now, even though there is some technical truth to this explanation, it kind of sidesteps all of the intuitive issues that are going on here. Yes, it is 100% technically true that even if I do this process for a billion iterations, if I took a microscope to that black shape, I would still see tiny little corners, and therefore it is never a circle. But the issue is most standard strategies for approximating pi rely on using shapes that look like circles but are also not circles. Let me just give you an example. So take a look at this construction here. I've drawn a circle and I've inscribed a square. And the big number in the middle is the perimeter of the square. So you can do this math on your own, or you could just trust me. Once again, the circle has radius 1/2. And what we're going to do is we're going to use a standard strategy for approximating pi. So what I'm going to do is I'm going to take the square and double the number of sides. I'm going to now make an octagon. When I make an octagon, you can see the perimeter has become a little closer to pi. Now for a 16 gone. Now for a 32 gone. Now for a 64. Now for 128. Now for 256. Now for 512. Now for 1024. And before you know it, you get something that looks a lot like pi. However, you could raise the same objection here that you did to the other one, because even though this is a 1024 gon and looks a lot like a circle, if you took a microscope to the shape, you would see that it is not actually a circle. So that explanation is bad because it doesn't really answer the question as to why is that one bad? Like, why is the pi equal 4 approximation bad? But how come this one works? Another thing I want to point out is that this seeming paradox has nothing to do with the fact that we are using circles. You can recreate this paradox using just a line. So this red line, say, that I've drawn here has a length of 1, and it's inside an equilateral triangle. So the sum of the lengths of these two black sides is 2. And you can use the same trick to show that 2 equals 1. Watch. So what I'm going to do is I'm going to make a little divot, It's sort of like you're taking the equilateral triangle and you're folding it down. So you're not changing the length of these two black line segments. And once again, you can do it again and again and again and again and again and again. And before you know it, you have something that is visually indistinguishable from a line, but you started from something that has a length of 2, and it's turned into something visually indistinguishable from a line segment of length 1. So why is this? Clearly, there's something deeper and more fundamental going on here that needs to be examined critically. Now, one thing that I noticed a lot online is that people were tremendously fixated on this idea of corners. They figured all of the issues in this paradox arose from the fact that we were trying to approximate things without corners with things that had corners. And I want to give you an example that will remove your fixation from corners. So look at this picture that I've drawn over here. Once again, you have a red circle with radius 1/2, and I have 8 black circles surrounding it. And what I'm going to do is I'm going to delete the inside of half of those circles and the outside of the other half. So it now looks something like this. Okay. Now, as you can see, this shape is smooth as butter. It has no corners whatsoever. And you should be able to compute its length. So I wanted to pick an example where you would not need any like calculus or whatever to compute its length. So this It should not be hard to compute this the length of this black shape. I'm just going to print it out over here. So that is the length of this shape. And just as before, you don't have to do this with just 8 circles. You can do it with 16 circles. You can do it with 32 circles. And more and more and more and more and more and more and more. And as you can see, once again, you eventually get something that is indistinguishable from a circle, but its length is nowhere near what it should be, which is pi. In fact, I believe it's pi square over 2 if you want to actually sit down and have some fun and do the math. Okay, so now to the actual explanation. And the simplest explanation I can give is that in math, just as in life, if you want to figure out how far you are going, the direction you are going really matters. So for example, let's say you have 2 ants, and from far away it looks like they're both walking from point A to point B. But one of the ants is walking in a straight line and the other one is completely drunk. It's like wiggling around, it's making lots of detours, but from far away it looks like it's basically traveling from point A to point B. Now, which ant do you think will cover more distance? Obviously the one that's drunk, because all of its little perturbations will cause it to cover way more distance on the way from point A to point B. So it really matters that the first ant is traveling in a straight line and the other ant is not. Now, just for your edification, let me show you what it looks like to travel around a circle at a constant speed. So this blue arrow is supposed to represent the direction that you are facing as you walk around the circle. And here's what it would look like. Amazing stuff. Now let's go back and revisit the example that actually worked. Now I hope you remember this example from earlier. This time, however, I'm going to show you what it looks like to travel at a constant speed along these black paths. So let's start with this one. When you hit a corner, you have to abruptly change direction. So there you go. There you go. There you go. And you are back home. Now let's do it again, except this time let's double the number of sides. Let's double the number of sides again. Now, it's a little jerky, but I hope you see what makes this particular approximation so wonderful. Not only is the black path getting closer and closer to the circle, like it's getting closer and closer to looking like a circle, but if you travel along this black path at a constant speed, say, your direction of travel also looks like it's getting closer and closer to what your direction of travel looked like when we were going at a constant speed around a circle. Now let's see if the same thing is true for some of the other examples I showed you earlier. Let's revisit this example real quick. So as you can see, this is what it looks like to travel along this black path. And it doesn't look anything like what it looks like to travel along a circle, but maybe it'll look better if we just increase the number of iterations here. So let's just bump it up by a bit. Let's see what it looks like to travel along this path. Uh-oh. This is even worse. It doesn't look anything like what it looks like to travel along a circle. So you can see the issue here. You can see why this is not as good a convergence as the example that actually worked. All right, so this video is getting long enough as it is. So to sum up, if you want to figure out the length of something by approximating it using other things, a good way to guarantee this is to ensure that not only do your approximations slowly look more and more like your final object, but also the velocity vectors, what it looks like to traverse your approximations also starts to look more and more like what it looks like to traverse your final object. That is a great way to guarantee it. If you only have that your objects just look more and more like your final object, it's the Wild West. I offer you no guarantees. Anything could happen. If you're a little bit more advanced, you may have noticed, by the way, that if you look at a technical definition of arc length, you may have noticed you'll see something like this in your physics or calculus textbook, and you are integrating the length of the velocity vector, and now you know just how essential it is to have that velocity vector there, because defining it this way ensures that any time spent meandering will add up. I hope you found that explanation crystal clear. Leave a like on this video if you did. Definitely leave a comment if you did not. I have no problem revisiting this issue. And I think that's all I have to say. So, peace.